Good morning. Obviously, it's not ideal that I'm not there to actually teach you this, and we can go over it quickly when I'm back. But what's important is that we crack on with Chemistry 2, and our aim is, remember, we're going to get this finished by Easter. So, what I need you to do in these next couple of lessons, while I wait for this nasty COVID to go away, is please do the following things. So when I'm going through things, listen, think about it. If you need to, ask who's covering the lesson to go back, listen again. And then what will happen now and again is they'll pause the video. So I will remind somebody when to pause it so that you can record whatever notes you need to, so that you have all the facts down, all the bits that you need to learn. And then if you're lucky enough to be covered by a science teacher, you've got somebody there to ask questions. You've got other people in the room you can ask for support. And actually, there's nothing wrong with you writing in the margin something that you're confused by or something that you want to ask me when I'm back. So I'm expecting, when I see you again next week or later this week, hopefully, I'm expecting you to have loads of questions. So what we were moving on to was rate of reaction. So when we talk about chemical reactions, we're talking about things in everyday life. And first thing I want you to do, I'm just going to ask whoever's covering to pause for a minute so you can look at these four so that you can put them in order of how long do they take. Which one is the fastest rate of reaction? Which one's the slowest? Okay, so hopefully you've got the fact that an explosion down here, you're looking at less than 1 second. So I'll put a 1s. You're looking at magnesium and reacting with acid. That takes a few minutes. Iron to go rusty. Iron starts showing rust after about 3 days. And then this statue, acid reacting with a statue and wearing it away over time, you're talking about many years. So reactions can be extremely, extremely fast, or they can be very, very slow and over a long period of time. We covered this briefly when I introduced the required practical last week when we were doing the acid and marble chips and you carried that out for yourself. And actually what we talked about was, get the pen in the right place, here's chemical A and here's chemical B. And if they're ever going to react, the first thing they have to do, I don't like the word fruitful, they need to have a successful collision. So chemical A collides with chemical B, and then they can react and form this new product over here. For that to happen, what must they do? They must be moving. If they're moving, they are then able to collide. But that collision must be successful. It needs to have enough energy to actually work and not just bounce off each other. So I'm going to ask whoever's covering the lesson to pause it and give you time to just write down the basics of what does collision theory mean for any chemical reaction. Okay, I'm hoping you've done that by now. So, for a chemical reaction to happen, again my pen's in the wrong place, for a chemical reaction to happen, reactant particles must something with each other, and that hopefully you're thinking is collide, and the particles must have enough energy when they collide. If they don't have enough energy, they just bounce off. A collision that produces a reaction is called a successful collision, and sometimes reactants can touch and not react, causing unsuccessful. And again, somebody will pause now so that you can make any notes you need to. Okay, So when we're talking about the rate of reaction, what we're actually talking about is measuring the amount of something. So the rate equals the amount, and we're dividing it by the time it took. Time in seconds usually. Amount could be in grams, it could be in milliliters of gas produced, could be something else. And on this page, it's just the main ways. So you don't need to draw all of these, but what we'll quickly go over is a reaction could change the pH. It could go from being acid to alkali or vice versa. A reaction, sometimes what we're looking for is we're looking for a colour change. And the faster the reaction happens, the faster it changes colour. So I'm just going to number these. Number 1, number 2, it could be a colour change. Number 3, and this is the one we did last week in a slightly different way. Number 3, they could release a gas, which comes over here, pushes this syringe, and actually we can collect the gas. So number 3, reactions could release a gas, which we can then measure. This one here at the bottom has a thermometer in it. So number 4, a reaction could be measured because it increases or decreases temperature. And number 5, this is deliberately up on the top of a weighing scales, because if this reaction was giving off a gas out the top, the scales would get lighter. So what we could record is we could record the mass and how much it's lost. If it's losing lots of mass, it's a fast reaction, and if it's losing a little bit, it's a slow reaction. So I'm going to pause there, and your little title for this bit is there, what types of changes could we measure? And there's 5 of them on the page there for you. So pause and record. Okay, so just want to quickly go over this. This one is what we did last week. We added some acid and marble chips together last Thursday. The gas that was collected came down this tube, it came up here, and we were able to read a measurement here. The other way of doing it is a gas syringe. Now, why didn't I get you to use a gas syringe? Number 1, they are very expensive. Number 2, they're made of glass. Number 3, they're easily broken. I'm not being cynical, we've only got a couple of them in the school, so actually it made more sense to do it this way in class than to do it this way. So this one is easy and simple to do, this one can be more accurate, but the equipment is a lot more expensive for it. Okay, so I'm going to change my pen if I can find it. When we looked at the reaction last week, this first bit here that I'm just drawing yellow next to, where it's a really steep gradient, it shows it's a really fast reaction. Whereas this bit up here, it's slowed down, and this bit here, well, nothing else is being produced over this side, so that means the reaction has stopped. So we go from here, we have a fast reaction. Here, it's slower. And here, it's stopped. So it may be that a lot of those particles that are colliding, here there's lots of particles, or they're close together or whatever. Here there's less particles, so the reaction slows down. And here, the reaction has stopped because all the particles of one of the chemicals have been used up. So what I'd like you to do is I would like you to sketch that graph neatly and make sure you're answering those questions, especially the first 2. So this one, when is the reaction fastest? And you can do it in labels on the graph. When is the reaction slowest? And don't worry so much about the bottom one. We'll do that in class. when I'm back. Okay, pause here and record, sketch, make notes. Okay, so here's two lines on the graph. What we have here is we have time going across the bottom, and we have mass or volume going up the side here. And that purple one here shows that the reaction starts off quicker and it gets to the end point here faster. This green line is just a slower reaction. I don't need you to do anything with this because you did this in the last lesson with our own experiment. So what we're moving on to now is how do we make a reaction faster? And it's exactly the same as how do we make collisions faster? What could we do to make those particles hit each other more often? And there are 5 different ways of doing it. Now the first one is we could increase temperature. So each of these 5 ways is going to be a little passage in your books. The first way we can make reactions faster is we increase the temperature. So these particles in the first diagram are moving quite slowly. Particles here are moving quicker. If you're moving quicker, then the chance of you colliding is higher. So it says here there are more frequent. So the chance of colliding is going to be greater because you're going to hit each other more often. And also, because you're moving faster, you have more energy. And if you've got more energy, more of the collisions that happen would be successful. Oh, 2 C's, 2 S's. Right. So, a little title about making reactions faster. Underneath it, number 1, temperature. And then can you draw some particles that are moving slowly, some that are moving quickly, 2 different colours. And then can you explain next to it what happens when you increase the temperature? So in industry, some chemical reactions, for example, the Haber process that we'll talk more about, that is carried out at 450 degrees. Why is it carried out at such a high temperature? Well, the answer is easy. At a really high temperature, the reaction is really, really fast. And it helps us make more of the product, which we can then sell. So pause now and I'll let you record that. Okay, so you've unpaused. Number 2 on our how do we make reactions faster is with a liquid, we can increase the concentration. You obviously can't increase the concentration of a solid or a gas, but with a liquid we can increase concentration. But the most important thing here is concentration. So on this side, this diagram shows for the green and red chemicals, there's only a low concentration. Maybe the rest of it is all water, and these are the 2 chemicals. If there are only a few particles, few molecules, there's only a few collisions, and the rate of reaction is, I'd say slow is better than low. On this side, there's loads more particles. If there's lots more there, there's a much greater chance of hitting each other and colliding, and therefore it gives a faster rate of reaction. So far, if we wanted to have a really fast reaction, we could have a high concentration and a high temperature. Okay, I'll let you pause there and record this section. Draw the diagrams, write notes next to it. Okay, number 3. Now, the concentration will only work for liquids. Number 3 is just for gases. because gases can be put under pressure. So what this is showing is the same number of particles here and here, but this time it's been put under pressure, so they've been squeezed closer together. So number 3, the particles are, number 3 is pressure. Here the particles are closer. If they're closer, they are more likely to collide. If they're more likely to collide, you're going to get a faster reaction. If you're trying to think about where we put things under pressure, think about a bike tyre or a car tyre. The gas is squeezed into a much smaller space than it would normally fit. So therefore it's under high pressure. That means the gas particles are closer together to each other, more chance of them hitting each other. Okay, somebody will have paused hopefully, and you can record this. Again, diagrams and notes. Number 4. Surface area. And this only works for solids. So we've had one for liquids with concentration, one for gases with pressure, and now we've got one for solids. If I take this big chunk here of chemical, the only place anything can collide with it is just on the outside surface. However, when I take the same size piece, so the mass stays the same, and I break it up, when I break it up, I increase the area. There's more surface. So if you look here, if you work through the maths for this one, the area works out as 24 centimeters squared, where other particles could collide with. When I cut it up more, it's 48 centimeters squared. The very strongest reactions would be got with a powder. Powders can react really quick because they have a massive surface area. There's much more surface in a powder, so other chemicals can collide with it quickly. So again, pause. Those 2 diagrams are a useful way of trying to remember it, that when you break something up, you make it have a higher area, as long as you keep the same mass. So pause it, diagrams, notes. And then last but not least, we have chemicals that are called a catalyst. Now a catalyst is a chemical that doesn't, there's a bracket by the way, doesn't take part in reaction. So this chemical is present, but it's unchanged, so it's still there at the end, so it doesn't actually take place and react. What this graph is trying to show, as time along the bottom here moves along, normally a reaction needs this much energy to be successful, this amount here, this black line, this hump. But with a catalyst, that energy is now much lower, it's only down to here. So all a catalyst do is they lower the energy needed to be a successful collision. So when they collide, they need energy, and a catalyst makes it so that even collisions with lower energy work. Okay, I'll let you sketch that out and then unpause and move on. So we have 5 factors: temperature, concentration, pressure, surface area, and catalyst. The whole idea is sometimes to make reactions as fast as possible. Where would that happen? Well, when in industry, when we want to make useful chemicals. Sometimes we want reactions to be fast to melt things together and produce lots of heat. Sometimes, with rusting, for example, we want reactions to be slow. So all we have to be able to do is explain in terms of particles why reactions can be fast or slow. Going to move straight on. So what I'd like you to do is, don't write it out like this. Increasing the surface area, choose whichever one you want to start with. So you might decide, oh, I'll start with, I like increasing temperature. What goes next to increasing temperature? If I increase the temperature, the reactants have more kinetic energy. So that goes second to it. If they have more energy, then more of the collisions are successful and they collide more frequently. So can you match up the rest of them? So pause now. And now you need to check your answers through. So are these the ones you got? So somebody can pause it and go on to that. And then the last thing for this video, I'd like you to try these 2 exam questions. Well, there's 4 on the right hand side and 1 on the left. The ones on the right hand side are easier worded, if that makes sense. So really quickly, question number 1 there. Oh, find my pen again. What's going to happen if you increase the surface area? What happens to a reaction rate if you decrease the pressure? Why does increasing concentration? So do those and then see if you can do the one in blue. Please write the question, maybe underline that at the top, then write the answers. Question and answer all the way through. Okay, hopefully now you've got great notes on this, ready for the next lesson.